Visualizing 10 dimensions is hard, and understanding the geometry of 10 dimensions is even harder. So in this video, I'm going to be describing random walks that take us across a 10-dimensional landscape, and we'll learn to visualize that and also to gain a little bit of an understanding. So what we're going to do, instead of jumping right to 10 dimensions, is we're going to start with 4D. And I think everyone has seen the 4-dimensional hypercube. And so what I'm showing here is going to be a 4-dimensional hyperlattice, but it's in high dimensions, and you can have a number of lattice points along each dimension. In this case, there are going to be 3 sites along each dimension. What we'll do is start with a ring of all the nodes and all the links for this 4-dimensional lattice, and then we're going to let this thing run and relax into a natural configuration. So here it goes. This algorithm balances a spring constant along the links against a Coulomb repulsion between the nodes. And so it relaxes into what looks like a 3-dimensional structure, but it's not. You can actually see that there are extra links. And so if you look at the number of links coming out of each node, it's exactly 4. And so this is a way of representing a 4-dimensional hyperlattice in just a 2-dimensional space. And this optimization algorithm, what it's doing is it's making it look like a 3D lattice, but really all the connectivity and all the nodes are behaving in just the way that a 4-dimensional hyperlattice would behave. Now we'll do the same thing for a 10-dimensional hypercube, and we'll let this run and relax. And here's the final representation for this 10-dimensional hypercube, represented as a network graph in 2 dimensions. It's a little hard to see the symmetry, the hypercube symmetry that's embedded in this, but each node has exactly 10 links to its neighbors, and this is a 10-dimensional hypercube, although rather compact. Now what we're interested in looking at is a random walk on this kind of a structure where you start a walker on one of the nodes, and then you just let them take random choices as to what directions they choose. Now in this case, they can choose one of 10 dimensions or 10 directions that they can take a step. And at each node, they flip a 10-sided coin and they make a decision as to whether to go in one dimension or direction or another. And over time, they will slowly drift away from their starting point in a process that mimics diffusion, but in this case, it's diffusion in 10 dimensions. Now we're letting the random walker take its steps, and each color on this graph as it evolves is a different direction or a different dimension. And it's just randomly choosing one direction over another, and as time goes on, it drifts farther and farther, on average, farther and farther away from the origin. Now we come to the idea of a landscape in high dimensions. So in this 10-dimensional hyperlattice, each node can have a value. It can be like a potential, or it can be like a fitness if it's a random walk through a genomic space for a species as it evolves. And the question is, if we require that the walker stays on a contour line, so a contour line is shown on the right, and it's a line of equal values that twists and turns through the high dimensional space. In this case, it's just shown in 2D, but there can be contours in high dimensions as well, and they actually have a mathematical name. It's called a level set. And so we can require that a random walker, when it moves or when it chooses its next step, that it is always going to a new node that has the same value as the current value within, let's say, some delta. And we can set that delta, so let's say 20% of the nodes are within the right range of a random walker. And so what that does is it means that only a subset can be accessed by a given walker. And that subset is a level set that spans through the entire space. And so you can have a random walker that, even though it's restricted in how many nodes it can go to because of the requirement that it has to stay on its level set, in fact, because of the percolation properties of high dimensions, it turns out that there is always, or almost always, going to be a spanning cluster no matter what level set you're on. Here is one of these level set subclusters, and we watch it evolving. And so this is a cluster which spans the entire 10-dimensional space. we can zoom in on this, and it may not look 10-dimensional. It really just looks like sort of spaghetti with globs, but in fact this is a level set which is spanning the entire 10-dimensional space. And we are once again interested in what would happen if we put a walker on this, and the walker will be able to span the space. And so it turns out that, very unlike 2 dimensions and 3 dimensions that we're so familiar with, in high dimensions you can almost always take a random walk that can span the full space. And it means that in high dimension optimization problems, and this includes problems of evolution, also problems in machine learning, it means that you can access virtually the full state space that is available. And it means that you can find optimal solutions. And it's one reason why machine learning and deep learning is so powerful. It's because of the geometry of high dimensions. Which brings us to the final conclusion, that in high-dimensional landscapes, mountain ridges are much more common than mountain peaks. And this has profound consequences for the evolution of life, the dynamics of complex systems, and the power of machine learning.